Okay, I'll talk about this new semi-analytical approach to do calculations of the radio emission from extensive air showers. This is how it's done today, at least for the macroscopic simulations. Both Zaires and Correas use something like this to calculate the contribution to the vector potential from a single track in the shower. So this could be like this is actually a very small track. It's like a step in the propagation of an electron in the shower. So you can imagine there are a gazillion of this to analyze and calculate the contribution. So the way it is now, we calculate the contribution for every single track. So here you have constants, you have the distance to your observer, you have the starting and ending times at the emission point, you have the energy, and here you have difference of these Heaviside step functions that basically gives you the time at the detector. These terms are really expensive because it has to do with the propagation time from the middle of the track to the observer, and it can be quickly approximated for vertical showers, but if you're going for more inclined ones, then it's a pain because it's really, really expensive, right? So, and also here you have what we usually call the compression factor. This goes to 0 if you see the shower at the Cherenkov angle, because everything arrives at the same time. But we do have a limit for this expression, so you end up with a delta. So that's what is done. We calculate heavy stuff for every single track in the shower. So the idea of this approach is actually very, very simple. So we divide the whole shower into 4D volumes of spatial size L and time length L over C. So we have to test these volumes to see if they obey the Fraunhofer condition, which is a condition for our simulation. So you have something like this. The side has to be much smaller than this, which depends, of course, in the frequency until which you want to be able to describe the emission. It also depends on, in this case here, R is the smallest distance, so the distance to the closest antenna. And of course, the observing angle, which we are very generous because we have to pre-calculate that. So the cell is sufficiently small so that many terms of that expression that I showed you before are constant for the whole cell, so that they don't have to be recalculated every time. But we still have many, many tracks inside the cell. So what we do, we calculate the contribution of all the tracks inside the cell for once for the whole cell, based on an average or an effective track that represents all the tracks that are inside of that 4D volume bin. So this amounts to almost a macroscopic treatment of the shower. These cells are macroscopic, but it retains the microscopic precision of the macroscopic approach that has been successful in this type of simulation. Okay, here I discuss a little bit how we divide the cells. We use something that's called octree binning. So we start with spatial cells that are really large, because if they are very far away from the observer, the Fraunhofer condition is very easy to satisfy. So we can start with very large volumes, far from the detector, and we test that for the Fraunhofer condition. So if the Fraunhofer condition is not satisfied, we just divide it into 8 smaller volumes. So we start with a big one. If it does not satisfy, we divide it into 8. So you end up with 8 new volumes. And we go on. So if, for example, this one does not satisfy, we divide it into 8 and so on. So once everything is divided and all the conditions are satisfied, we then do the heavy stuff, which is the calculation of that effective refractive index, that integral. And we just calculate it once per cell and store it. so we can use it later. Here is how we calculate like the average or effective track inside that volume, and we calculate the contribution to the vector potential. So, as I said, all tracks inside that volume are represented by a single effective track. So if you have these tracks here, I have a track in purple here that is an effective track that takes into account all the tracks inside the volume. And then I do the calculation just once for the whole cell using that average track. This expression here is in a different notation, but I promise you it's completely equivalent to that expression that I showed in the first slide. The only difference here is that instead of the quantities of the track, I have these two quantities here, which is Q vector V here, and this temporal effective temporal here, which is calculated like this and completely defines this average track. So it's basically an average of the timing of the tracks inside the volume and information about the direction and the speed of the tracks inside that volume. So you just calculate everything. This is equivalent to that compression factor. This is equivalent to the beta perpendicular that you saw before. So we just apply basically the same formalism to calculate, but only once. Then we have to add the contributions of each of these cells into a histogram for the detector. This is done in a very similar way as Zaires and I imagine Corbeas does. So you have that boxcar function, which gives you like a window, a time window at the detector. So the contribution to the vector potential is this. And then we just, the bins that fully overlap get the full contribution. And in this case here, that the overlap is just 1/4, you get 1/4 of the contribution and so on. This is the same in Zaires. So here we took a few tracks, well, many tracks from a Zaires simulation with very low thinning because these files are really huge and we just want to compare the two methods. And here's a comparison between a full simulation with that ZHS or Zaires formalism in orange here, and this approach which is in blue. You can see that the vector potential is pretty well in agreement using both formalisms. This is the spectrum that you get after this, and you see that up to a certain frequency, around 80 megahertz here, you can describe very okay-ish the results if you compare the results of this approach with Zaires. So it's looking good. Now I want to emphasize the importance of the correct cell sizing, because if you have a cell size that's too large, you get something that has nothing to do with your pulse. Here I'm showing the pulse, bandpass filtered pulse, also using the same tracks that I saved. You see if the cell is too large, it has nothing to do with the pulse, and as the cells get more and more correct, you see that I get closer and closer to the full Zaires results. So it's very important to do this cell sizing correctly. Here's the same thing, but with the spectrum. If I have a huge cell size, then I get away from the Zaires results even before I reach the beginning of my bandwidth. And as I go to smaller and smaller cells, then I can go further and further. Here would be enough for a regular simulation. And if you go still further and reduce the size, I can go to higher and higher frequencies and use that. This, we didn't expect this to be very well represented because this is the full bandwidth pulse. So we know that we have a limit, a frequency limit for this approach. But if you get small enough cells, you can pretty much describe a little bit, even the full bandwidth pulse. So what are the advantages of this method? It's basically, it should be much, much cheaper computationally. So because we only need a single calculation per for the volume. So the heavy stuff is done only once. So theoretically, it's much faster. As I said, it's an almost microscopic approach, but it retains the formalism of the microscopic approach that has been working so well. And because it's macroscopic, maybe we can devise some kind of parameterizations for the average track. So we have like a representative to do some calculations. We can also substitute the star-shaped approach for interpolation. So usually when you want for reconstructions, you need the field everywhere, or you need several positions to do some minimization or something like that. You usually do a simulation with antennas in a perpendicular plane. And then if you need the field somewhere else, you just interpolate the results you have at that plane. In this case here, if you use, you have to be sure you satisfy the Fraunhofer condition, which depends on this distance to the antenna, to the closest antenna. If instead you do a little bit further and do the distance to the ground, then you ensure that this condition is satisfied for any antenna that you can put in the ground. So at the end, you have all the average tracks that you have from the simulation. You have all these cells, you can save it all, and use it later to quickly calculate the trace anywhere on the ground. So this could, in principle, substitute this type of interpolations. Also, and very much important, that's something, if you do like a track-by-track calculation, there are some very heavy calculations that you actually cannot do, because if you do it on a track-by-track basis, it's too expensive. But here with the cells, we can do these calculations because we have so many cells and that's it. So stuff like atmospheric effects can be calculated in advance for each cell. So we can take into account some kind of curved propagation and other kind of effects. And these effects are really important, especially for upgoing horizontal showers and in the case of satellite or balloon experiments. Another thing that we could add that usually is done after the full simulation is done, and we take as an arrival direction to take into account antenna patterns, we just take Xmax and say that the whole radiation is coming from there. But here we can do it by cell. So you have the correct antenna patterns for the beginning, middle, and end of the shower.